Hi everyone, we're Fluoride Gravity team, and I'm Chang, this is Cheer, and that's Kevin. As our fluoride has expanded to new locations, new problems pop up as we're treating different types of water. For example, India is located on a fluoride belt, and so naturally there's a high content of fluoride in their groundwater, and as about 14% of the Earth's crust fluoride content is located in India. And India is also highly dependent on groundwater, with more than 80% of water is used as groundwater is consumed. And the problem with high fluoride contents in water is that overconsumption of fluoride can lead to a lot of health problems. For example, more common cases are dental fluorosis, as shown as the picture on the left, and more severe cases can be skeletal fluorosis, or even more severe crippling bone deformities, as you can see in this picture. The goals for our team this semester is to improve our gravity power system to be as compact as possible and for it to be easily operated in the field. And also, we would like to create a fabrication or operation manual that can be helpful for future reference and future field testing. Our team uses a coagulant flocculation and sedimentation process to treat our fluoride. And so with fluoride-rich water, we add coagulants into the system for it to react with water and form flocks. As the flocks grow bigger, the aluminum hydroxide fluoride precipitates will be settled in the sedimentation tank, and while the treated water with fluoride removed will exit from the effluent. The pictures show that how we adjusted the dimension of our system to make it as compact as possible. For our fluoride concentration, we made the stock concentration the same as we want to be in our system concentration. However, for our pack coagulant concentration, we made our pack stock concentration is constant throughout the entire time, while we adjusted the system concentration of coagulants by adjusting the flow rates of the coagulants line. And for example, if we increase the coagulant flow rate in our system, we will increase the system concentration of coagulants in our system.
So now for the total system flow rate, that flow rate is governed mainly by the height difference between the top of the fluoride tank and the point where the effluent tube is at. And so what we've done is we've put the effluent tube on these adjustable sliders that allow us to very easily change this value delta H, and so therefore control the flow rate very effectively and easily. And so for the coagulant flow rate, we first had to find what our system concentration was going to be, what the concentration of our stock solution for coagulant was going to be. And the way that we did that was that we had to take a number of parameters, and the first being that we could not exceed a maximum pack flow rate of about 10% of the system flow rate. The second parameter was that we did not want to be under 0.0015 milliliters per second, because then that would be difficult to measure with the methods that we were going to use. We also had a predetermined system flow rate that we used and a maximum pack concentration based on previous fluoride work. And so that helped us determine our stock concentration of 2,500 milligrams per liter, and then that allowed us to define the window of flow rates that we wanted for our total experiments, and those being between 0.0015 and 0.015 milliliters per second. And so the way that we measured flow rate was with first initially a scale, which allowed us to measure the mass rate of change between as pack moved from the top to the bottom, constant head tank. But this was a concern because the float valve that controlled this flow was not sensitive enough to the small flow rate. And so therefore we thought that it would be a good idea to implement the IV drip chamber, which gives us a visualization of what the flow rate is going to be. So not only is it easy for us to measure, it will be also very easy for people in the field to measure. And so this is what we use to then calculate a set of standards. So we would calculate the flow rate at different heights. And so the first test that we did, we've created this first graph, but then saw that the flow rate changed very drastically with a small change in height. And so we had about a 5 centimeter change in height, and we saw a very big increase in flow rate. And so in order to solve this problem, we added longer microbore tubing to increase the head loss, and then that allowed the slope to decrease to a value that we were comfortable working with. And but that was not the only problem. One of the problems that we found later on was that there was constantly air buildup in our system, and we hypothesized that this was caused by the 90-degree elbow that we had at our pack connected to the IV drip chamber. So then we straightened that out, and we took that off and drilled a hole through the stage to allow it to hang freely. But the problem was still consistently happening, and so we discovered that the way to solve this was to add a ball valve and a choke to prevent any flow from water to escaping, and which prevented air from entering the system and not giving us inconsistent value between tests.
After accounting for these inconsistencies, we measured the flow rate empirically to establish a linear relationship between the system pack concentration and height. So what we did is we marked different heights and counted the amount of drops per time to get a flow rate, and then we used the equation we got to calculate the height needed for desired system pack concentration. So after establishing a reasonable height and pack flow rate, we ran preliminary experiments with fluoride and pack to test the usability of the system. A couple problems we ran into is when we were starting the gravity apparatus from an empty system, the air bubbles became trapped in the set tank and the flocculator, and this prevented flow through the system. So what we had to do with that is we ran a water pump to force water through the system and push the air bubbles out to allow the system to flow. The other issue we ran into is that there were air bubbles in the microbore tubing, which prevented flow out of the drip chamber. So in order to account for that, we had to take the air bubbles out. The last problem we ran into is that the probe we purchased at the start of the summer was no longer accurate. We found out that fluoride probes have a lifespan of around 6 months. So for future experiments, we need to use a new probe we bought, which is the whole primary fluoride probe. A couple things we found out this semester are that the length of the microbore tubing can be changed to control the change in flow rate versus height and allow for more precision. We also learned that the IV drip chamber is an effective way to measure the flow rate. One thing we found out is we established a height and flow rate linear relationship, and we did this using the IV drip chamber. We also found out that reproducibility between the tests is a challenge because when there's air bubbles in the system, this affects the flow rate and height relationship. A couple of things that future teams can work on is improving the flow rate reproducibility, as we mentioned before. Another thing is we can run more tests with fluoride and pack, and we also need to compare the results we get from our gravity apparatus to the automated pump system. Ultimately, our goal is to create a field test apparatus. We also need to optimize the startup procedure. The process of filling up the set tank and flocculator and the drip chamber flow could be made more user-friendly.